So in this recording, I'm going to continue looking at section 8.1. In the first video, I talked about the basics of linear inequalities, solving inequalities, things like that. Oops, didn't mean to write that. I also looked at the different ways of expressing your solution sets. So either graphically, as you can see I've done here, or using SetBuilder notation as I've done here and here, or using interval notation as I've shown here and here. So here's the graphing on a number line, and here's the interval notations here. So today what I want to do in this video is talk about the main topic of this section. All of that was really review. So the main topic of this section is actually, how do we solve compound inequalities? And these are inequalities that show two different constraints on a variable. So for example, something like x is greater than 3 and x is less than or equal to 8. Or x is greater than or equal to 6, or x is greater than or equal to 8. Okay? You'll notice that these two different constraints on the variable are joined by either the word and or the word or. And these words have different meanings, both in life and in mathematics. And so I want to address each of them. We're going to start out by addressing the ones that have the word and in between. So when you have the word and in between two simple linear inequalities like this, you are only interested in the solutions that satisfy both of the inequalities. And that means you're looking for where the two sets, those two solution sets, the solution set of the first inequality and the solution set of the second inequality, you're looking for solutions that are in both of those sets. So that's where the two sets would overlap. And the technical math term for that is intersection. So we're going to be looking for the intersection of our two sets. So if you think about, this first circle here being the set A and the second circle here being the set B, the numbers that, or the elements, because they don't always have to be numbers. In this class, they'll mostly be numbers, but in life, it doesn't have to be just numbers. So anything that's in set A, I'm shading kind of like that with red. Anything that's in set B, I'm going to shade in the other direction with green, right, like that. And so those elements or numbers or whatever they are that are in both sets are those that are in here. This is where the two sets are overlapping. This is where we saw both of the shadings occurring, right? So the intersection is the set, that's supposed to be set, of all, sometimes this just looks too messy for me. There we go. Of all elements, and by elements, most of the time I'm talking about numbers in this class, right? I'll just put that in parentheses. That are in both sets. Okay, now there is one symbol that I want you guys to take a look at, and it's this symbol right here, right? So this symbol refers to the intersection of two sets. Okay, and again, The solutions of the intersection of two sets will be those solutions that are in both sets. So we're going to do a simple sort of numerical inequality, or not inequality, but intersection problem first, okay? So this says find A, and then remember this symbol means intersect, right? Intersection of. So this is saying the intersection of sets A and B. So find the intersection of the sets A and B if the set A contains these numbers, 1, 2, 5, and 7, and the set B contains these numbers, 2, 7, 8, and 9, right? So what I want is only the numbers that are in both sets. That's what intersection is. Whoops. And so the intersection of set A and set B will contain, well, let's see, which numbers are in both sets, right? Well, set A has a 1, but set B doesn't. Set A has a 2, and set B also has a 2. So that's in both sets. That belongs in the intersection. Let's see if there's any more. So there's a 5 in set A, but there's no 5 in set B. There's a 7 in set A. Oh, and there's a 7 in set B. So that's in both, right? And that kind of finishes off what's in set A. Set B also has an 8 and a 9, but those are not in set A, so they would not be in the intersection either. So the intersection of two sets are just those elements that are in both sets, right? They have to be in the first set, and they also have to be in the second set. Okay, and that's why that word "and" is used to represent intersection. And that's actually what you see happening in B, right? So here we have the word "and" in between. And that word "and" is referring to the intersection of these two solution sets. Okay, and that's the first thing to notice about example 2. So what I want to do is I want to look at these two solution sets. So I have the set that contains all the numbers, all the real numbers x that are, and then this is the greater than symbol when you read it from left to right, okay? So all the real numbers x that are greater than 3, all right? So why don't we go ahead and represent those on a number line so we can see that solution set. So I'm going to do that one. Let's say I'll do that one in, I'm going to do it fairly light. I'm going to do it in this sort of soft pink. No, it's too soft. I do it in this deeper pink color. Okay, so, and I blew it because I also want to put my 3 and 8 on my number line. And I'm putting both 3 and 8 because those are the numbers that are the sort of the dividers between those numbers that do satisfy and don't satisfy each of these inequalities. So now I'll go back to that pink. All right, so the first set is all those numbers that are greater than 3. So here's the 3 on my number line, right? And I want to make sure that I'm only shading those numbers that will satisfy this. Numbers that when I plug them in for x, substitute them for x, will satisfy this inequality. So the numbers that will satisfy this are any numbers that are bigger than 3, like 3.1 or 4 or 17 1/3 or 25.57, right? Like any numbers that are where with respect to the 3 on the number line? Well, to the right, okay? So that first set, and there's no part of an equal sign there, it's just greater than. So 3 itself would not satisfy this. If I put the 3 in for x, it would say 3 is greater than 3, and that's not correct. So I'm just going to use a parentheses at the 3, and I will be shading off to the right. All right, now I'm going to take a different color, and I think I'm going to take this bright green, and I'm going to take a look at those numbers that satisfy the second inequality. And the second inequality says that x could be any real number, so x could be any number that is less than or equal to 8. Okay, so where are the numbers located that will satisfy this? Where are the numbers that are indeed less than or equal to 8? Well, first of all, 8 itself, the boundary number 8, right? That will satisfy this because of the or equal to. It would say 8, is less than or equal to 8, and that's true. So 8 does have to be part of the solution set because it satisfies this inequality. Where are the rest of the numbers, though? Are they to the left of 8 or are they to the right of 8, right? Well, any numbers that are less than 8 are numbers that are smaller than 8, right? So those numbers that are smaller than 8 will be to the left of 8 on my number line. So for this one, I'm going to want to shade to the left of 8. But I'm also including 8 in my solution set, so I'm going to use a square bracket to represent that. Okay? Okay, so this is what the two separate inequalities look like when I graph them sort of above the same number line, right? So on this number line, what I'm going to do is now graph the solution of this problem, which will be the intersection, because that's what that word and in between means. So what I really want to do is just shade those numbers that are in both solution sets, right? Well, if you think about the fact that this number line is sort of being divided into 3 different areas, there's this area to the left of 3, there's this area between the 3 and the 8, and then there's this area that's off to the right of 8, right? So this region over that's to the left of 3, right? These numbers are parts of the first solution set because that green shading, no, of the second solution set, because that green shading does extend to the left of the 3. So these numbers are in the green solution set, which is the solution set for the second inequality here. But they are not in the purpley solution set, which is the solution set for the first inequality. So that means these numbers are in one of the two sets, but they are not in both of the sets. So these numbers over here will not get shaded in my intersection of the two solution sets. Okay. Likewise, the numbers that are to the right of 8 are in this purpley solution set, which is the solution set for x is greater than 3, but they are not shaded in green, which would make them these numbers that are not solutions of this second inequality, which says that x has to be less than or equal to 8. These numbers are not less than or equal to 8. These are, in fact, greater than or equal to 8, right? To the right of 8. So these numbers over here are not in both solution sets. They're only in one of them. So they will not be in the intersection of the two solution sets either, okay? So the only numbers that are in both solution sets, right, are those numbers between the 3 and the 8. Those are shaded in green from the second solution set, and those are shaded in purpley color that are solutions to the first inequality, right? So in between the 3 and the 8, these are the only numbers that are in both solution sets. So what I really want to do is, I'll put my intersection down below. I want it to go from 3 to 8, right? And I want to use the same closures as are happening at the 3 above and at the 8 above. Because remember, 3 is not a part of the purple solution set, but it is a part of the green solution set. So it's not a part of both. Therefore, I want to make sure it's not included in the intersection by using that parentheses. The 8 is actually a solution of both because it's shaded in the purple, and it's also included because of the square bracket here, which is because of that or equal to, part of the less than or equal to symbol, right? This bracket indicates that it's included in the green set, and there's a line that goes straight through the purple. So this is a number 8 that is actually in both solution sets, so I want to use my square bracket. And so for my final, and so this is actually where, like my scratch paper, it's where I figured out what that intersection was going to be. But the final intersection is actually just what I have down here. So I'm going to put that on my final solution set graph here. So I have my 3 and my 8, and then the 3 will have the parentheses, the 8 will have the square bracket, and then I will shade just in between them. Okay? Now, I also have to write this solution set in the other 2 formats. One of them is SetBuilder Notation, where I use the set bracket followed by the variable. My variable name here is x. And then I have my such that bar. And now I need a single inequality for this set of numbers. And you may recall that when you have this interval where there's a definite numerical beginning and a definite numerical ending, and it's shaded in between those two, you may remember that those inequalities look like this, where you have the small number on the left, the variable in the middle, and the big number on the right. And it's always either a less than, an is less than symbol, or an is less than or equal to symbol in both places. So that's what I'm going to be doing down below in example 2. And so here it's going to be 3, then x, then 8. So you do so all these numbers in between are like your values of x, right? And you don't need to write that x right there, but I'm just trying to show you that these are all the values that x could be that will satisfy both of the original inequalities that are in the intersection of those 2 original inequalities. Because there's a parentheses here, 3 would not satisfy this inequality, so I do not want to have an or equal to, so I'm just going to use the less than symbol there. And because I have a square bracket here, 8 would satisfy this inequality, so I do want to have that part of an equal sign there, so it'll be is less than or equal to. And then I close my set bracket. So the way we read this again is, because of these set brackets, we read it as the set of all real numbers x, such that x is between 3 and 8, not including the 3, right? And that's the way we can read this. You could also read this as 3 is less than x and x is less than or equal to 8. Or you can read this as x is greater than 3, because I'm reading it backwards since I started with x. X is greater than 3, and x is also less than or equal to 8, right? But it's always going to be written with these less than or equal to symbols. Never a greater than or equal to symbol. Okay, interval notation, remember, has the smallest number in the set first, followed by a comma and the largest number in the set, right? So the smallest number in my set here is 3, but it's not included. So I'll keep that same parentheses there to show that it's not included in the solution set. The largest number in my set is 8, and it is included as evidenced by this bracket. So I'll keep that bracket in my interval notation too. So this is what interval notation looks like. And the way we read this is the set of all real numbers from 3 up to 8, not including the 3, but yes, including the 8. Okay, so that is our first example where we were solving a compound inequality, and that is where we have 2 inequalities with the word and in between them, joining them together. And the word and, remember, means that you're going to be looking for the intersection of those 2 individual sets. So what I did, just to recap, is I graphed the 2 individual sets first, and then I looked for the numbers that are in both sets. So where does the shading overlap? Where do these 2 sets of numbers intersect? And in this case, it was between the 3 and the 8, not including the 3, but yes, including the 8. Okay, so then I draw out my graph. So I don't show the scratch paper stuff. I only show that intersection, which is this part of the graph right down here, right? And then I wrote SetBuilder notation and interval notation for that. All right, I think I have to do one more here before I'm going to stop because I have a live session to do. So this one says we're going to solve this compound inequality, and we're going to graph the solution set and write it in both SetBuilder and interval notation again. So this one is actually a little bit more difficult than the previous one because this one has two inequalities here joined by the word and, so it's still going to be an intersection. Oops. There we go. So we're still talking about the intersection of these two solution sets that was supposed to be there. But these two inequalities have not been solved for the variable yet. So we have to solve each of these first. So I'm going to use two different colors for this. So I think I'm going to use that kind of purple color. And so I'm going to, in the first one, begin by moving the constant 6 to the other side. So now I have 2x is greater than or equal to 10 minus 6 is 4. And then I'm going to divide both sides by 2. So I'm going to have x is greater than or equal to 2, right? And the next one, I'm going to change colors on this. I'll make it in green. In order to solve for x, I'm just going to have to divide away this coefficient of -3. So this time I'm going to be dividing both sides by a -3, which is a negative number. And I'm hoping that you guys recognize that that is going to require me to change the direction of my inequality symbol, right? Because here I divided by a negative number. And anytime you divide or multiply both sides by a negative number, you have to remember to change the direction of your inequality symbol. You have to reverse it because dividing or multiplying by a negative actually gives you the opposite of what the real solution set is. And -12 divided by -3 is +4. So those are my two solution sets, but remember they do still have that word and in between them, okay? So what I'm going to do is graph each of those solution sets individually on my number line. So the first one, actually, first of all, let's mark these numbers. I have a 2 and a 4. Make sure you put them in numerical order, right, on your number line. So smaller numbers on the left, larger numbers on the right. Sometimes students get these mixed up. And if you get those mixed up, it becomes a big, big problem. Okay, so now I'm going to go ahead and graph this first solution set. I'll use the same color. So it's this purple color. So it says x has to be greater than or equal to 2. So where are the numbers that are greater than 2 located? Are they to the left of 2 or are they to the right of 2? Well, numbers that are greater than 2 are to the right of 2. As long as your variable is written first, you can actually just use the inequality symbol as a directional arrow telling you which way to shade, right? But your x has to come first. Your variable has to come first. So this says that x has to be greater than or equal to 2. So I will be shading to the right of 2. And because of the or equal to, I want to include 2 in my solution set by using that square bracket. All right, I'm going to switch colors. Whoops, didn't mean to do that. Okay, and this time I'm going to graph the solution set of x is greater than 4. So numbers that are greater than 4 will be numbers that are to the right of 4. Again, this inequality symbol is greater than can actually be thought of as sort of a directional arrow telling you to shade to the right because it's pointing to the right, but that's only because the variable came first. So I'm going to shade to the right of the 4, but I'm not going to include the 4 in that solution set. I'm using parentheses because there is no part of an equal sign here. 4 itself would not satisfy this if I substituted it in for x. 4 is not greater than or greater than 4, okay? All right, now before I move on to my final solution set, I still have to tackle the main purpose of this problem, which is this guy right up here. I've got to find the intersection of these two sets. right? So the intersection of these two sets of numbers is going to be, where do the two shadings both occur? Where do they overlap? What do they have in common, right? Well, once again, these two numbers on the number line kind of split this number line up into three regions. I've got this region, or this area, that's off to the left of 2. I've got the between 2 and 4, and I've got to the right of 4. There is no shading to the left of 2, so that's not an either set, and therefore cannot be in the intersection of the two sets. This region between the 2 and the 4 is shaded by one of the two colors, but not both. And remember, intersection means only the numbers that are in both sets, right? The numbers between 2 and 4 are in one set, but not both sets. So they will not be in the intersection either. It is only those numbers that are to the right of 4 that are in both solution sets. You can see that they are shaded in green and they are shaded in the purple. So this part right here is my intersection. And because of the parentheses here, I'm going to mimic that. So it'll have the parentheses, and then we will shade off to the right. Okay, so that's to the right of 4. So when I write my final solution set, I really only need to have my 4 on here. Now, that's not to say you can't have 2 or 1, 2, 3, 4, 5, 6, 7 labeled on your number line. It's just not necessary to mark more than just the 4. I know that there are plenty of numbers to the left and there are plenty of numbers to the right, but the 4 is the one that matters. That is the number that is the boundary line between those numbers that do satisfy the intersection of these two sets and those numbers that don't satisfy the intersection of these two sets. So I just want to shade to the right, so I'm going to shade off to the right, show that it's going out there forever. And again, I'm using that parentheses because the 4 satisfies one of the inequalities but not both. Okay, so it doesn't belong in the intersection because the intersection only includes those numbers that are in both sets. So that's what my graph would look like on a number line. In SetBuilder notation, I would have the set that contains all real numbers x such that, and now I need an inequality to represent just this set of numbers. I don't want both of these. I don't want the 2 originals. I don't want the both of these. I just want a single inequality to represent this solution set, because this is one set of numbers. It's one continuous set of numbers, so I only need one inequality. Okay, these are all the numbers that are to the right of 4, and numbers to the right of 4 are those numbers that are greater than 4. So it'll actually be just this one, x is greater than 4, right? X is greater than 4. All right, for SetBuilder notation, the smallest number in our set where the shading begins is 4, but 4 is not included in the solution set, so I use that parentheses again. And then I have a comma, and after that I'm supposed to put the largest number in the solution set. But this solution set keeps getting larger and larger. The arrow to the right indicates that it always continues to get larger. All of the numbers that are to the right there are going to be solutions of this compound inequality. And so how do I represent that? Well, I use the positive infinity symbol. So I'm going to use positive infinity here. And we always use parentheses with either positive infinity or negative infinity. That is that notation. Okay, so as much as I want to continue, I'm going to stop here, and I will make another video to continue. All right, good luck.